Basically, what I was intending to do in my talk is to try to answer this question that is very important for Lev, and I think that when trying to answer it, it will touch be the source of some of my disagreements that I had with Lev during the short period we were working together just before the COVID. But then I'm just thinking in light of this last talk by David, which is super relevant, you could also read what I'm trying to say as a careful way of motivating this way of dealing with underdetermination by expanding the empirical context. So basically my talk is not going to be much about the in-depth many-world interpretation, because I think that the answer to this question, why is it not a consensus, it has to do more about consensus and in what case we should have it than with the details of the many worlds interpretation itself. So for example, if we would be presented with a perfectly good solution to the probability problem of an explanation of the Born rule, I think we still wouldn't want to have it a consensus, and I'll try to explain why. So let me just note that Lev is not the only one that would like to have a consensus. So for example, this is from the blog of Sean Carroll, who says, so the title of the blog post is "The Most Embarrassing Graph in Modern Physics," and the embarrassing thing is that we don't have an agreement, and this is from the same post. He's citing the poll by Schlossauer, Koffler, and Zeilinger, which I think it's a smaller poll that just preceded the one that was cited at the beginning with the 6%. So this one has only 33 participants of a workshop. Then, okay, let me start by saying a few words about general considerations about consensus. Then we have, of course, many reasons to pursue consensus. And there is the view that pursuit of consensus is what makes science, that's what makes science rational, and that also makes people trust in science. And we would also, or at least many of us would like to avoid relativism. And why not try to aim for consensus? Then we would also want to avoid dogmatism. And if we studied philosophy of science, then we would expect some unavoidable degree of underdetermination. For example, due to the Duhem quantities and other reasons. And I don't take this kind of underdetermination to be necessarily such a strict anti-realist thing, but just you could view it as some moderate anti-realist. So it rules out only very strong versions of realism, just as a necessary consequence of doing science. So these are very general considerations, and then we could talk about more local considerations to the question of quantum mechanics. Well, we would want to have a consensus in the context of quantum mechanics, because this is not just a generic underdetermination. We have huge differences. It's a completely different universe if we are talking about many worlds or if we're talking about objective collapse. So this is something that we would better agree on, because it's such a fundamental difference. But then on the other hand, maybe just in this particular case, we are not able to facilitate a consensus that is based on evidence, and maybe this is why we shouldn't aim for consensus. So these are the general considerations. Basically, what I would like to argue about is theoretical virtues and the role. And I would like to argue that based on basically a philosophy of science that is done in the context of discovery. Basically, the theoretical virtues are good for theorizing, but the history of science teaches us that they are very shaky ground for ontological belief and consensus, and in particular, the advance of science requires us to be fallibilist towards whatever it is that theoretical virtues tell us. So I will say a bit more in the end what do I mean by that. So let me start. Basically, I'm going to briefly talk about two debates, the ontology of space and the ontology of electromagnetic fields. So about space, there is the famous, maybe most famous debate in the context of classical physics, then Newton thought that his theory requires absolute space in some sense, and for Leibniz, this sort of absolute space, it shouldn't, it makes no sense, and he was trying to read it in a different, in a relationist way. And then one way to read Ernst Mach's criticism is that unobservable absolute space is actually not required for Newton because we have the Earth, we have celestial objects, and everything basically is with respect to those observable objects. So just to formulate this debate in a way that is a little bit more similar to the debate in quantum mechanics, let me add one more step here, which has basically nothing to do, or very little to do, with these conceptual and ontological questions. In the late 18th century, there is a beautiful historical paper by Meli, I think it's Domenico Meli, which describes the introduction of coordinate systems and reference frames into physics. Basically, let us remember that Newton did not use X, Y, and Z, did not write sigma F equals MA in the way that we write it today. So these coordinate systems enter physics later as mathematical devices in the case of rotating systems, rotating tubes, for example, and the solar systems and various other systems. And so that was something which was, first of all, entered physics as a piece of useful mathematics. And then later on, here there was philosophy. The positivists wanted to get rid of the absolute space, so they tried to give it an operational meaning, so at least, so maybe things are not absolutely accelerating with respect to absolute space. Like we can just, like Ludwig Lange suggested in inertial frames, we just throw three free particles, we don't exert any force on them, and then these free particles would define a frame, a coordinatization of space and time. And this would operationally define the inertial frame, which replaces absolute space. So now I would like to take the perspective, which is just before general relativity. It doesn't matter that much if we are before or after special relativity, and ask what are our options to understand inertial frames. So one way we could say, well, those inertial frames are the mathematical representation of absolute space, so we could be more careful and say, well, we're only justified in regarding them as representation of affine connection over Galilean space-time, which basically defines trajectories moving at absolute velocities, but there is no absolute rest. Or we can, following Mach, regard these inertial frames as the influence of celestial bodies or a universal center of mass. And if we are going into special relativity, then we can regard those inertial frames as a representation of the Minkowskian geometry of space-time, or we have the more recent line of thought, symmetries of the dynamics, like Harvey Brown and others. And I think that if, so these are many of the options, probably not the only ones, and we can choose between them based on theoretical virtues. So for example, for Mach it was observability. The positivists in Mach's time, before the logical positivism, they did not want to have unobservable explanans. They want the explanans to be as observable as the explanandum. And there is locality, because Newton in the Gravitazione, he actually considered the possibility of the influence of the celestial bodies, and he rejected it because it was not local. And there is a parsimony, which is a more moderate version. So we can have, maybe we can put something unobservable in your theories, but we should be careful and not do it more than we need to. And I think that if we take the theoretical virtues based on which Lev, for example, justifies the many worlds interpretations, then maybe the most plausible one would be the Minkowskian geometry of space-time. This is what, it's local, it gives us a very straightforward and clear explanation. And if this is the case, then we would read it in this particular way. But now let's talk just at the very early development of general relativity. So this is Einstein 1907. This is the first paragraph in this paper, in this paper is starting to develop GR 2 years after special relativity. And this is the first paragraph in the part that relates to GR. So far, we have applied the principle of relativity, the assumption that the physical laws are independent of the state of motion of the reference system only to unaccelerated reference system. Let us now try to apply them to accelerated relative, to accelerated frames. And then later on in his late reconstructions, he's also emphasizing this point. So the equivalence of inertia and gravity is the happiest thought of his life. But why is it so happy? Not just because it is not talking about unification at all. It is a happy thought because it can help us get rid of those inertial frames that we don't want in physics. And then in the famous 1919 in the London Times, he's saying very explicitly, just between, this is a paragraph, between the special relativity and the general relativity, what has nature to do with our coordinate system and the state of motion, we need to get rid of those. The point is that Einstein chose this research project of getting rid of inertial frames in 1907, and he pursued it for 8 years. But this move would have made no sense if we have a consensus over inertial frames that are so significant that they represent the fundamental, the fundamental structure of space-time. So I think that here we should also be more careful. So for example, if this wasn't a research project that Einstein would have been able to pursue by himself, if he needed to write a grant and build a particle accelerator or whatever, then maybe it would have been rejected just because we need those inertial frames as a part of our ontology. Why try to get rid of them? So basically, theoretical virtues are important here, but they are important for theorizing. We reject a good theory that is working perfectly based on a theoretical, we're theoretically, or Einstein was theoretically, he had this discomfort with it. So in this case, the theoretical virtues did their job, but not in the context of interpretation. Now, just a little bit on the interpretation of electromagnetic fields. Interpretation of electromagnetism, early interpretations, there is very little literature in comparing with the literature on space. So this is, I found this, very recent Oxford handbook on the philosophy of quantum interpretation. It just came out this year and it looks very promising. There is also an entry by Valia on collapse theories. But there is also this beautiful paper which makes a point much in the spirit of what I'm trying to say about analogy between interpretation of quantum theory and interpretation of electromagnetism. And they're arguing that Maxwell introduced into electromagnetism this separation between what we would call, maybe some of us would call today, the separation between interpretation and between the theory and its interpretation, or between formalism and theory. So Maxwell introduced it, but he did not realize he introduced it, and Hertz noticed it. And following their paper, I went to read Heinrich Hertz from electric waves. So he says that Maxwell's theory is Maxwell's system of equations. Every theory which leads to the same system of equations is Maxwell's theory. And there could be different theories leading, or what we would maybe would say different interpretations leading to the same theory. And when we see bodies, what are the possible theories? When we see bodies acting upon one another at a distance, we can form for ourselves various conceptions of the nature of this action. We may regard the effect as being that of action at a distance, or we may regard it as a consequence of action which is propagated from point to point in a physical medium. He then introduces 4 theories, 4 possibilities. The first one is the action at a distance. We regard the attraction of 2 bodies as a kind of spiritual affinity between them. I'll skip the second and third, which are somewhere in between. The first standpoint is the familiar field standpoint, which he argues that it is Maxwell's standpoint, and this is also the standpoint on which he's going to base his report on basically the theory and his observation of electric waves are included there. And there are theoretical virtues at play. There is locality, which we can read here. Leave no room for doubting that Maxwell wished to discard distance forces entirely. And then there is a parsimony right here below. I've endeavored in this exposition to limit as far as possible the number of those conceptions which are arbitrarily introduced by us. So, so try to keep it to the fields, and then somewhere else, he and also Heaviside in parallel, they realized that it's possible to formulate classical electromagnetism without the potentials, so we don't need them, they're just helpful things. But then let's now go back to Einstein's introducing special relativity. So this is the case. There are asymmetries in the equations which are not asymmetries in the phenomena. For example, if we put the magnet into this coil, then the change in magnetic field over the coil will induce this electric field, and this electric field will exert a force, and then we'll have a current. But then if we'll do it the other way around and move the coil, then the magnetic field is going to be constant. We don't even need Maxwell's equation in this case. It's just the Lorentz force equation. We have basically the electrons are moving in the magnetic field, and this is why we're going to have an electric current. So, and then the point is that here again, if we have a consensus that electric field or something, and magnetic field or something real is in a medium, this move would have made no sense at all, because today we are used to thinking about it in terms of this electromagnetic tensor, which has this observer relative existence. But then in 1905, before Einstein, if we believe in the existence of electric field and a magnetic field, then it would just make no sense. Then, just to finish, I would like to say a few words about the Aharonov-Bohm effect. I think that the Aharonov-Bohm effect is basically a different case, and we'll bring it as example of something different. So it has its own interpretational debate, which I'm not going to go into, but I think that the Aharonov-Bohm effect does have significance that should be uncontroversial, in the sense that in classical physics, so we can look at this particular, observable. So this particular observable is an observable also in classical electromagnetism, if we understand it as sum over the influence of the field, of the magnetic field inside. But in quantum physics, we can measure it even if we don't have access to the inside, to the field itself. So this is basically, this is before interpretation. We realize that quantum mechanics allows us to measure something that we couldn't measure before. Now, the reason that I'm using this particular formulation, so this integral is not from Aharonov-Bohm paper. It's from Erwin Schrödinger paper in 1922. So this is even before quantum mechanics. This integral was written with this peculiar definition of gamma that we don't use this symbol anymore in this context. But it's exactly the same integral if you take it to be a closed integral. And the reason I'm showing it here is that when we are reading Schrödinger, just 4 years later, would come up with his equation that together with what he was doing here in this 1922 paper, in the context of old quantum theory, could basically lead him straight away to the Aharonov-Bohm effect. I think there are other pathways that could have led to the Aharonov-Bohm effect. So when reading Fritz London, when reading also later textbooks on quantum electrodynamics by Dirac, by Pauli, you're reading them, just 2 more sentences and you're in the Aharonov-Bohm effect, but then nobody realized it until 1959. Not exact. Ehrenberg and Sidai did suggest the same experiment in 1949, and they said, well, just at the end of their paper about diffraction, optics, they said something, well, this is strange that it depends on the flux and not on the change of the flux, and then nobody cared. And then I want to suggest that maybe the reason that Aharonov-Bohm effect was not discovered for so long, and it was ignored when it was, in a sense, discovered, it may be because of this kind of dogmatism, that we know that these fields are the real thing, we don't need to think about the potentials, and until Aharonov-Bohm just said it explicitly, significance of the electromagnetic potentials in quantum theory, then nobody thought it's basically an option. So just to conclude, I think that we should use theoretical virtues, first of all, in theorizing and not in building a consensus, and we should be fallibilist with respect to them. So, and then when we have a problem with theoretical virtues, then this tells us that we should revise our theories and we should improve them, or at least that we should try. And these improvements come at the interface of two theories, right? Which, like, this is the case of all three examples. And then, sadly, we also see that these new successful theories, they do not resolve the interpretational debate, but they do teach us, we learn, we gain new knowledge, and we completely reshape the landscape of possible ontologies. And I was hoping this, and I think they should hope and try that this will also be the case here. So basically, I'm arguing that if we want to learn the lesson, then we should also understand the measurement problem as something which calls us to improve our physics, a problem our physics, not a problem in our understanding. And then we look to for solution or for way to move forward in the interface with other theories. Then basically the project that David just described is just one of them. Personally, I think that the understanding the interpretational possibilities in quantum field theory is just beginning, even though the theory is not new at all. We have very little idea about how we could interpret it, and then maybe we have definitely reasons to hope that this will also teach us about the measurement problem and maybe even just lead to completely new possibilities that we did not think of yet. Thank you.
Thank you. I'm wondering about the boundary between physics and understanding here. I mean, so the case study I have in mind is decoherence theory. So in a certain sense, decoherence theory doesn't take us beyond the underlying equations we had. I mean, you can do decoherence theory in QFT and things, but mostly we've explored it in the non-relativistic domain. And decoherence theory has certainly transformed our understanding of the average interpretation. But in some sense, it feels as if that counts as changing our physics, not just our understanding. I just wonder what you think about cases like that.
Yeah, it's a good point. So when I first came across decoherence theory, I felt it really. That's right. That's another thing that it took a long time to realize. And this is one possibility of identifying, for example, macroscopic object within this quantum physics. And then definitely, that's also true. So maybe these things sometimes, very rarely happens also within a theory. You don't have to go to the interface just because it's such a complicated theory. I mean, right, so you don't have to go to the interface sometimes.
Thank you, Guy. Just to say, I do think that evoking historical studies is, it may be that it doesn't give you quite what you think, and if you look at it again, perhaps other lessons can be drawn, and of course it depends what areas you look at. So I just want to, this thing you've got on the top right, a problem in physics, not in our understanding, and this is somehow a lesson you're drawing in general. But to take, let's just take electromagnetism. It seems to me that there was a problem of intelligibility in electromagnetism running through the 19th century. And that problem took the form of a quest for an underlying ether that would be subject to Newtonian principles and so forth. In a sense, you might conclude, well, it had to be modified. And sure, we went to quantum electromagnetism, but I don't think that assisted with the intelligibility. I think something else really happened over the course of about 120 years or so, from about 1800 through to 1920, where we no longer sought the kind of intelligibility we thought we had to seek, something like that. And I think that would put a rather different light on what lessons we should learn from history. So, I mean, another example, of course, might be action at a distance, and this was thought unintelligible, and for 100 years, from 1680s and so forth, it was thought to be unintelligible. Eventually, it became the paradigm of what was intelligible and so forth. I mean, you might think this is grist to your mill because we modified the physics in that case to get Einsteinian gravity, which was a local theory. But I don't think actually that we any longer think Newtonian gravity is unintelligible. That's not. So I just suspect there's another thing running through this history of physics bound up with preconceived standards or conceptions of what is intelligibility and so on and so forth that typically just eventually go away.
Thanks, very good point. So just let me just put it on the table. I think that in my opinion, so learning from past physics, I see it as one mission of philosophers of physics, because historians usually, they don't want to do it. They're on the fine details, and physicists, well, obviously they cannot do it by themselves. They need us, philosophers. So this is what, and of course, whenever we do it, we express an opinion. This is philosophy. So this is one thing to be clear. But of course, there is a limit to how far we can learn from history, just because maybe this time, this case is different. We're now dealing with a different physical case. There is obviously a limit to what degree we can learn from history. But I think that we can learn about ourselves and question whether should we have a consensus in this kind of particular situation, then that's not only about the world, it's also about ourselves. And in these cases, we can learn from history. And all I was trying to say here is don't run too fast to have a consensus over the best theory. Maybe later on we will have physics would suggest different options, and this consensus might actually hinder our way to newer physics. And you're absolutely right that the mathematization of physics in the last century fundamentally changed things in the standards of intelligibility that we seek, definitely. And this is basically something that should be carefully studied, I think, by philosophers, this change of standards. But nevertheless, I think that this argument against consensus still stands. So even in the clear case of electromagnetic field and absolute space, if there the consensus might have been misleading, then obviously here, in this case, which is much more puzzling.
One last question.
I just want to make a suggestion that actually there's a lot to learn from history, but something a little different than you're pointing out. And I don't know this Hertz paper, right? But just from what you flashed up there, it looks to me like Hertz his own thing is internally inconsistent. Let me say why. He says, well, any theory that gives you Maxwell's equation, that's Maxwell's theory, right? And then you go down and there's this whole issue. Now, suppose I say, all right, here's my theory. I try to be very precise. I believe the fundamental things are the vector and scalar potentials in Coulomb gauge fix. Okay, normally what we would say is, all right, your theory now is really non-local in the sense of instantaneous action, right? I move this guy and your physical thing you just postulated arbitrarily far away instantaneously changes. But of course, from that theory and some definitions, I can give you Maxwell's equations, right? So, I mean, he's not even clear about his own. I think what it shows you is that these foundational and ontological questions are very complicated and tricky and have subtleties to them which a standard physics education doesn't prepare you for, right? It can prepare you to do good math, and it can prepare you to, the kinds of discussions we're having, you're just not well prepared. And I think you see that through all history. I mean, think of the consensus that atomism was nonsense because you couldn't observe the atoms.
Atom. Mm-hmm.
Atomism, I mean, go back to the debate about atomism, and people, again, from a kind of operational point of view, well, if you can't see them, blah, 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 well, the atomic theory was correct. So, I think it's certainly true you shouldn't place too much emphasis on consensus, you should worry about why people are forming the views they're forming and put on the table as explicitly as possible what the considerations are that people are using. Because I think there's all kinds of confusion between people. They don't communicate well. They're fuzzy in their own heads. And just taking a survey, sociological survey, is not of any use for physics. It's just for sociology.
So I think what Hertz is doing here is beautiful, because in a sense he's very careful, and let's not make it a semantic argument. So he's saying, well, we can derive everything from Maxwell equations, but there are different ways we can get to them and different ways we can think about them, and maybe there is a spiritual affinity between particles, and then these electromagnetic fields are a bookkeeping device, and then Wheeler and Feynman suggested something in 49 in the same spirit. And maybe we should be realists about these fields. So we're just putting on the table 4, what we would say, ontologies that are consistent with evidence. And evidence is easily, in his way of thinking, is easily connected with Maxwell's systems of equations. And this, I think, is very justifiably being careful, and it seems that later on, so this 4th standpoint became, in a way, a consensus. But I think it's very good that these were laid on the table from the first place, and physicists or anyone thinking about it should have these 4 options in mind.